Okay, so I left you talking about cinder cones in the last video. I was saying that most of the material that they do produce is cinder sized. They have typically very steep slopes of degrees between 30 and 40. They have a very large and deep crater relative to their overall size. So you're seeing the crater right here. It's very large and also looks like it's very deep compared to the overall size of the volcano cone. They're nearly symmetrical, but yet you still see an elongated side on the side where the wind was blowing during the last eruption. So from this picture, I think that the wind was probably blowing on this side, but it's hard to tell if that is correct based on the aerial picture. But let's assume that it was. The wind was blowing on this side, so it doesn't make it quite symmetrical per se. They're mostly produced by a single or a short-lived eruptive event. So a study that was done on cinder cones showed that 50% of them were built in less than a month. So all of that material was created by eruptions that happened in less than a month. Maybe just one single eruption, or maybe many of them, but just in 1 month. And 95% of all cinder cones were made in less than 1 year. So there are a few exceptions, of course, like for example Paricutin in Mexico, which I think was erupting for 10 years if I'm not wrong, or close to that. And also Cerro Negro in Nicaragua, which I think has been active for about 20 years or so. They're also usually small features due to their short lifespan. So because they don't last very long, they don't have a lot of time to build up in size. So when you compare them, for example, here in the bottom image to shield volcanoes, they're absolutely minimal. They tend to be about a kilometer or not even that big. There's actually one cinder cone a bit northwest of Mountain Home, now that I think about it. If you're ever around the area and you want to check it out, it's pretty visible when you're driving towards Mountain Home from Boise area. As you know, it looks like a volcano but smaller. And if you drive just maybe 5 or 6 miles down the road, that I think is one of those exits, maybe exit 85 or so, you can check it out. It's called cinder cone, no wonder. So usually cinder cones are scattered throughout the world, but there are certain locations that are concentrated with them, like the volcanic field near Flagstaff in Arizona, for example. Okay, so lastly we'll look at the third type of volcano, or cone I should say, volcano cone. These are called composite volcanoes, also named stratovolcanoes. I'll try to refer to them as composite volcanoes, but I may alternate, so beware. Again, composite or stratovolcanoes. So they tend to be the Earth's most picturesque, but also very, very potentially dangerous volcanoes. Most of them are located in the narrow zone that rims the Pacific Ocean, which is called the Ring of Fire, and we'll expand on this towards the end of lecture. Classic stratovolcanoes are large, nearly symmetrical, composed of a pyroclastic material interbedded with lava flows, like the idealistic anatomy of a volcano that we saw before, like this one over here. So you see lava flows kind of buried in between pyroclastic material that was built up. A few volcanoes like Mount Etna and Mount Stromboli in Italy show very persistent activity with molten lava inside their craters, which is not very common. For example, Mount Etna has erupted an average once every 2 years since 1979, so it's very constant activity, and you see the actual lava on the crater, which is not very common. Their shape, their conic shape, is attributed to their relatively high viscosity lava flows that actually do flow, if they flow at all. Let's see, so as we had said, those flows don't tend to go very far, and not very fast. So the material builds up the steeper side to those cones. Their slope itself is usually between 20 to 30 degrees, with a slightly steeper summit towards the end, towards the summit. And they are usually medium in size, but still about 1 to 10 kilometers in length. So as you're seeing again, comparing the more composite-like cone, like Mount Rainier is, to the shield volcano, it's still a lot smaller, but it is definitely much larger than the cinder cone type of volcano. They tend to be active for fairly long periods of time, much longer than cinder cones for sure, usually on the order of hundreds to thousands of years. Places where these are characteristic are, again, all around the Pacific Ocean, in the Cascades, the Andes Mountains. They're also in Indonesia and in the Philippines and in Japan, in the Aleutian Islands in Alaska, and there's also some in the northern coast of the Mediterranean Sea. So those aren't associated with the Ring of Fire, but they are associated with convergence of two different plates. Alright, so with that, we're gonna continue the discussion talking about eruption size and the different types of hazards that come from volcanic eruptions. So the eruption size does matter when it comes to volcanic eruptions. The image on the left is quite good at displaying the volume that has been erupted from various well-known volcanic eruptions in the recent and further past. So when you compare Mount St. Helens, for example, right here, to Mount Pinatubo, the overall volume of erupted material is less than 1/10 that of Mount Pinatubo, which happened in the Philippines in 1991. And when you compare it to, for example, the volume that was erupted by the Yellowstone caldera, the last eruption of the Yellowstone caldera, it's really about 1/1000th of the volume that was erupted by Yellowstone, or even less than that, I suppose. Okay. And the largest eruption that we can deduce in the last 0.1 million years is the Toba eruption that occurred 75,000 years ago. So right here. So again, those aerial images show you the scale that we have right here for what is remaining of the crater lake and resurgent dome inside of that lake. So you see the lake that is remaining from the crater, and we'll look at how that occurs, and then the resurgent dome that is forming right inside of the lake. You can see the 20 kilometers for scale right here. So overall, the lake is probably 35 kilometers wide and about, I would say, 70 kilometers long or so. The Toba catastrophe hypothesis suggests that this eruption actually caused a volcanic winter of 6 to 10 years, and possibly a 1,000-year cooling episode. This is just a hypothesis, so it can't be proven, but it is also hypothesized that, or I guess it could, potentially in the future we could prove it, but again, it has also been hypothesized based on this Toba eruption, that it caused a population bottleneck for us humans, meaning that the population size reduced greatly. It reduced to between 10,000 to 30,000 individuals when this eruption occurred. Again, this and the climate effects of said eruption are still being debated. There's no clear idea that that is exactly what happened. Okay, so now we are going to talk about volcanic hazards. And more specifically in this slide, we'll talk about pyroclastic flows. Roughly about 1,500 of Earth's known volcanoes have erupted at least once, and some of them have erupted several times in the past 10,000 years, which is when we have pretty much historic records of them. About 70 volcanic eruptions can be expected each year on Earth, and one large volume eruption can be expected every 10 years. About 500 million of people currently live exposed to relatively immediate volcanic hazards. And those areas are in Indonesia, and the Philippines, in Italy, and in Oregon and Washington, for example. Again, half a billion people. So again, we'll look at pyroclastic flows as one of the hazards first. So pyroclastic flows are some of the most destructive forces of nature, and they consist of hot gases that are infused with incandescent ash and larger lava fragments. They can race to speeds that exceed 100 kilometers per hour down the volcanic slopes. So they're definitely fearful. Or they should be feared. The flows themselves have two main parts: a density cloud of these hot expanding gases that contains the fine ash particles, and they have also a ground hogging portion, so one that remains closer to the ground, which is composed of pumice and other vesicular pyroclastic material, so a little bit heavier than just simply the ash and the finer gas particles. The hot gases that are released after the eruption inside of the lava fragments, they will expand and reduce the friction between the ash and the pumice fragments, which gravity then propels downslope in a nearly frictionless environment, which is why many deposits that are found so far from the source can occur so far from the source, because in fact there is basically no friction in the environment due to that rising of temperatures. Typically, these pyroclastic flows are generated by the collapse of tall eruption columns during an explosive event. Once the gravity overcomes the initial upward thrust that is provided by the escaping gases, then gravity will itself send very large volumes or amounts of this incandescent blocks and ash and pumice downslope. The images on the bottom show pyroclastic flows from the 1984 Mount Mayon eruption in the Philippines. So here they're pointing out the pyroclastic flows. The more ground hugging part is kind of imperceptible in the image, but it is right there. And then this is the more airy part that has the ash within it. Again, the more bottom one has the pumice and the blocks and the bombs that are being erupted and now are falling. The top two images point out the number of cascade volcanoes that are or have been active in the past. So you're seeing here all of the different volcanoes that form part of that cascade volcanic arc. All of these have shown explosive behaviors or will show explosive behaviors based on the environment that they're in and the composition of the observed magmas and the observed material that has erupted from them. So they are definitely a potential for pyroclastic flows in the future.